Hey everyone. In class today we left off making some contour maps. If you are in second period you can skip ahead a little bit. We already did these, but 8th period we didn't quite get as far. So I'm going to start on example 2 in the 14.1 day 2 notes. We're going to sketch the level curves of our function f of xy equals x squared plus y squared for our k values of 0, 1, 4, and 9. Something to notice about these k values is they're not evenly spaced. So this contour map with only these 4 level curves that we're going to be drawing actually does not give a good idea of the steepness of the function, unless you think about how it takes the z values longer or shorter to change their value between an equidistant amount of like x/y distance. So remember, we're just substituting in these k values for z. And when I say z, remember, we can write, instead of f of xy, we can write z equals x squared plus y squared. So I'm going to make a quick table over here for k values and then the equations that we get when we substitute in those values for z for our level curves. So that would be x squared plus y squared equals 0, x squared plus y squared equals 1, x squared plus y squared equals 4, and x squared plus y squared equals 9. We know how to draw all of these. 3 of them are circles. This first one, there's only actually one point where this is true, which is the origin on the xy plane. So I'll start with that one. I'll draw my level curve, which is that point at 0, 0. And then I'm going to need to draw a circle of radius 1 and 2 and 3. And man, drawing circles never goes super well for me, so hopefully yours look a little bit more circly than mine do. But we do the best that we can. So there are my level curves. I do expect you to label them. In this case, I'm going to use some lines/arrows to help me label that that is the one for k equals 9, that is the one for k equals 4, that is the one for k equals 1, and that point right there is for k equals 0. So if we were to take each of those level curves and raise it to the z value that is given by our value of k, that's going to start giving you this idea of what this three-dimensional graph is going to be looking like. All right, I have another example where we're going to sketch the level curves for our hemisphere. If you'd like to try this one yourself, you can pause and give it a shot, see what it looks like. Or you could just continue watching me. So I like to think about this graph. I know it's z equals the square root of 9 minus x squared minus y squared. It's helpful to think about this function as z squared equals 9 minus x squared minus y squared, where we're only going to be able to take positive z values. And rearranging things, if we like plug in k, to make it easy for us to draw, we get x squared plus y squared equals 9 minus k squared. And that equation right there is going to help us draw our level curves so we know exactly what they look like. You will notice for this question that the values of k that we're substituting in are equidistant from each other. So the closeness, or how far apart the level curves actually are, will give you an idea of where the function is steeper and where we say it is flatter. So k equals 0, 1, 2, and 3 are the ones that we're doing. That gives us x squared plus y squared equals 9. Because we're not working with perfect squares this time, I am going to use 2 of these markings on the graph to represent a distance of 1 so that it's easier to draw some of these decimals that we're going to be working with. So the first level curve is x squared plus y squared equals 9, which is a circle of radius 3. And of course, the bigger I make these things, the harder it is for me to draw something that actually looks like a good circle. But again, you know, we should do our best. So there is our first level curve for k equals 0. When k equals 1, there's going to be x squared plus y squared equals 9 minus 1 squared, which is 8. There's a circle of radius square root of 8, which I believe the square root of 8 is going to be closer to 3 than it is to 2. So I'm going to kind of take a guess that maybe square root of 8 is somewhere right there. I could, you know, take out a calculator, be less lazy, and get the actual decimal to get a better approximation for where it is than just guessing, but I think this will do the trick for now in giving us an idea of these being just kind of close to each other. So that one right there is k equals 1. Go back to my chart here. When k equals 2, x squared plus y squared equals 9 minus 2 squared, which is 5. So that's a circle centered at 0, 0, radius square root of 5, which is a little bigger than 2, because square root of 5 is going to be bigger than square root of 4. So maybe I'll put that one maybe a little past my values of 2 around my circle here. And then again, sketch a circle to the best of your ability to. Okay, not great, but you get the idea. There is k equals 2. And then finally, when k equals 3, that is going to be x squared plus y squared equals 9 minus 9. So that's 0. So we're back to a point right here. So that is k equals 3. You will notice that around the outer level curve here, that the level curves are a little bit tighter together. That means in this area right here, it takes us less distance to travel in the x or y direction to go, in this case, up a value of z, which means that it is steeper around the edge here of the hemisphere when we're closer to the x, y plane. Let's write ourselves a note, is that we're kind of steeper here, and then maybe like flatter up here near the top of it. Okay, I think we're moving on to the next one. This is where I did leave off for second period. Ooh, sorry. My cat is jumping on my papers. Apologies. All right. Sketch the level curves for x squared minus 4y squared equals z. You might notice that this is one of our quadric surfaces. It's our hyperbolic paraboloid. But let's look at our level curves for 0, plus or minus 4, and plus or minus 16. When k equals 0, so that's the number we're substituting in for z, we get x squared minus 4y squared equals 0. We can actually get y by itself here to give us an idea of what this looks like as a picture. So we get x squared equals 4y squared. I would divide by 4 and take a square root, so we get y equals plus or minus 1/2 x. So my first two level curves for when k is 0 is actually a pair of lines. I'm going to go up by 2's on my graph again to represent distance of 1. So to graph the line y equals plus or minus 1/2 x, we just need to go our slope of 1 up 2 over and over again And even though we're not going up by like ones on our graph, that doesn't matter. The slope still acts the same way no matter how we have organized our axes, as long as they're equidistant. So these are the times where I wish I had a ruler that I could set on my computer screen to give you some slightly better visuals. If you check out my completed notes on the calendar, that I did spend some time making sure the graphs looked extra nice for this one, so you could check those out if you want to see this looking very nice. So those both deal with when k is equal to 0. What happens when k is equal to 4? That gives us our level curve x squared minus 4y squared equals 4. You might recognize this as the equation of a hyperbola. If I divide by 4, we get x squared over 4 minus y squared equals 1. That is a hyperbola that opens in the x direction. And remember, to draw this thing on our axis, we're going to go out 2 in the x direction, we're going to go out 1 in the y direction, because those are the numbers in the denominators that are squared. We're going to think about a box that deals with those. We can put asymptotes between the corners, and then we can plot the vertices of the hyperbola, but the rest you kind of just have follow. The rest you have follow the asymptotes, which happens to be the lines that we've already actually drawn. Remember, because x is positive in this case, that we're going to be opening in the x direction. So our vertex, because the denominator of the x squared is 4, the vertex is going to be at x equals 2 and x equals negative 2. And we are going to just follow where our asymptotes would be, which again happens to be the lines we have already drawn. If you need to draw the whole box to understand that, please do so. When k equals negative 4, I need to label my level curves. When k equals negative 4, we get x squared minus 4y squared equals negative 4. How is this different? When we divide by negative 4, it's just going to change which of the two things is positive and negative. So we get y squared minus x over 4 equals 1, which is still a hyperbola, but now it's going to open in the y direction. The asymptotes are still the same for this one. We just, because we're opening in the y direction, we need to put our vertex a distance away from the center of whatever's underneath the y squared, which is 1 squared. So we're going to go 1 in the y direction. We're going to go 1 in the positive y direction, excuse me, in the negative y direction. And from there, you draw your hyperbola that, again, gets close to the lines, which are our asymptotes. So write something like that. And that is for our k equals negative 4. All right, I'm going to go a little quicker through the 16s now, giving you the idea with the 4s. You should be able to, I'm imagining, follow along a little quicker here. X squared minus y squared equals 16, and x squared minus 4y squared. Sorry, I think I said y squared above. X squared minus 4y squared equals negative 16, which leads us to x squared over 16 minus y squared over 4 equals 1, and x squared, oh, just kidding, let's put the positive thing in front. Y squared over 4 minus x squared over 16 equals 1. So again, we're still going to have the same types of asymptotes a little bit here. I'm going to be a little lazier when I draw these things. You could make your box by going out 4 in the x direction, 4 in the x direction, 2 in the y direction, 2 in the y direction, making your box, drawing your asymptotes there. You'll notice that the slopes of those is still 1/2. We just have a pair of hyperbolas, one that'll open in the x direction with the vertex at x equals 4 and negative 4. It is for our level curve at k equals 16. K equals 16. Right there. And then we have the one for negative 16, which is going to have vertices on the y-axis at 2 and negative 2. Okay, so there are our level curves for our Pringle. Let's think about the connections between the contour plot and the actual hyperbolic paraboloid. If I'm at the origin and move along the positive or negative x-axis, the value of z, so if you can see the three-dimensional graph here, there's the x-axis that way. From or traveling along the x-axis direction, you'll notice that z is growing, is increasing. So z increases. If we move along the y direction, though, which is this way right here, you'll notice that we fall down on the saddle. So that is the value of z decreases. This makes sense since you get a parabolic trace of opposite signs when x and y are fixed, creating the saddle-like shape. So we have a kind of upwards parabola here that I've kind of sketched in blue. Hard to see, I know. And then we have a downward-facing parabola going in the y direction, the other way there. So we get kind of like this interlocking set of parabolic traces. And eventually, later this chapter, we'll talk about saddle points. You can tell saddle points from contour plots. If you think about this thing right here, we talked about how like a point with a circle kind of thing around it kind of tells you that you're probably going to have a max or a min. If you have a point that has lines going through it and things kind of radiating out away from it, those are normally our saddle points. And we'll talk way more about saddle points in the future. All right, let's keep going without further ado. For some purposes, a contour map is more useful than a graph. The figure below shows some computer-generated level curves together with corresponding computer-generated graphs. So you have this function right here whose level curves are given right there. This can sometimes be more helpful in understanding what the graph is doing depending on the viewpoint that you have of the graph. Like if you just saw this one, it's kind of hard to tell what the graph of that function xy e to the negative x squared minus y squared actually looks like. Where on our level curves, we can kind of tell that we might have some maxes and mins. It looks like there is some symmetry about the graph. Of course, without the labels, I can't tell what's positive and negative z, but things kind of look very similar. We get steeper in these areas right here where the level curves are really close together. It looks like as we're getting away from the origin on the xy plane, it looks like things are spreading out a little bit, getting flatter, so on and so forth. Notice that the level curves in part C crowd together near the origin. That corresponds to the fact that the graph in part D, so we're down here now, I'm sorry, is very steep near the origin. So again, looking at this graph, kind of hard to tell what's going on sometimes depending on your viewpoint. The level curves give us an idea that we look like we have some kind of symmetry. We have steep spot right there. I kind of see some circles around like a point that might not be drawn, but that kind of makes me think I might have max or mins. And yeah, that is the function z equals negative 3y over x squared plus y squared plus 1. All right, let's talk about some useful contour maps. A contour map is also useful for estimating function values. Example 4 says a contour map of a function f is shown below. Use it to estimate the values of f of 1, 3 and f of 4, 5. Remember that this f of 1, 3 is a ordered pair 1, 3 being plugged into this function. So if we look at our contour map, which is the x-axis and y-axis right here, if we find the point 1, 3 right here, it looks like we're pretty close to this contour line right there. And based upon the label, it looks like we are near 70. And even though we're not on 70, it looks like we're between a contour that is 70 and a contour that has a value of 80. So, I don't know, our point looks a little bit closer, maybe, to the 70 contour. So I'm going to go with f of 1, 3 is approximately, maybe I'll do 72. We know f of 1.3 lies between level curves with z-values 70 and 80. So I know that they should be between those two numbers. To me, it looks like it's closer to 70, so a value closer to 70 would make more sense. If you want to try the next one, I would pause this really quick and see what you come up with. I'm going to show you on the contour map where 4, 5 is. Look at what contours we are between. So it kind of looks like f of 4, 5 lies between level curves with z-values of, looks like 50 and 60. We're kind of middle-ish. Maybe a little closer to 60. So maybe if I'm estimating, maybe a good estimate would be like 56 or something like that. Just an estimate though. If you wrote something down different, that's kind of close to that, we are okay. All right, level surfaces for functions of 3 or more variables. It is very difficult to visualize a function of 3 variables by its graph, since that would lie in 4-dimensional space. However, we do gain some insight into f by examining its projected level surfaces, which are the surfaces with equations f of x, y, z equals k, where k is constant. If the point x, y, z moves along a level surface, the value of f of x, y, z remains fixed. So the main difference from our contour maps in 3 dimensions versus this 4-dimensional thing is that a 3D graph is a surface that has projected 2D level curves, where a 4D graph projects 3D level surfaces. So that would be f of xy equals k. K is a value, so we have a function of 2 variables, so we look at it in 2 dimensions, versus f of xyz equaling k, a constant, which is something with 3 variables equaling to a value. So that it would be a 3D graph. And we can use those projections to help us understand a graph in 4 dimensions, even if we can't see the actual graph in 4 dimensions itself. So let's do some level surfaces. Let's say we have the function f of x, y, z equals x squared plus y squared plus z squared. In words, drawing our level surfaces where we're going to have x squared plus y squared plus z squared equals k. That is a family of concentric spheres with radius square root of k. And that's our visual down here, is that depending on the value that we're assigning k, we have level surfaces, which, how do you extend that to the 4th dimension visually? We really don't. But this would be the shadow. This set of concentric spheres is the shadow of something in the 4th dimension. A little weird to think about, I might imagine you would say. Let's move on to the next one. F of x, y, z equals x squared minus y minus z squared. The level surfaces would be x squared minus y minus z squared equals k. And if we rearranged to get like y by itself, that would be y
equals x squared minus z squared minus k, and you might recognize the quadric surface here. This is a family of hyperbolic paraboloids. So again, I can't really ask you to draw this so much, especially this one. Maybe the spheres, maybe a little, but I'm sure the picture would look bad. But we have our shadow of our fourth dimensional graph here, which is a family of Pringles getting stacked in the y direction. So if we could extend each of those three-dimensional points to a fourth dimension to give a value, that's how we would try to graph this. But man, oh man, it's really hard to kind of understand what that actually means. Okay, thank you for watching if you did. Let's see. You're going to probably see an email for a second here. No, we didn't. So we're going to look at the calendar. I'm going to be posting this video on the calendar. You have a card sort right here that if you want to get some practice going on matching graphs and contour maps and equations, you can try that out right there. Sign in. I don't care if you use like a sign in. If you log in, you can save your progress, so that's generally a good thing to do. But there are two card sorts in this where you're imagining equations, contour maps, and functions. I know there's a lot of things right here, so if you're like a little overwhelmed, start stacking some of them just to hide them a little bit until you're like ready to get to those things. If you go on to the next page, it will tell you how many cards are sorted correctly, and then you can list things here if you want to see what other people have to say. And there's a second one right here with some different functions, different graphs, and different contour maps. And if you click on the cards, you do get to see a slightly bigger version right there if you don't remember ever doing that. And again, you have a slide that tells you how many are matched correct, and then some lists, some things that helped you do that. I think we'll talk about this a little bit on Tuesday. If you are interested in thinking about the fourth dimension, I have a link here of an article that, if it's not going to show me visuals, I'm not going to be happy. But if you want to read about the hypercube, which is our quote-unquote cube in the fourth dimension, we have ways of modeling this thing in 3 dimensions, and you can read about what's going on with three-dimensional projections, three-dimensional shadows of a fourth-dimensional graph. I think this is an interesting read, so that is on the calendar for you to check out if you are at all interested. After the long weekend, we'll come back on Tuesday. I'll check in to see how the level curves thing went for you all, and then we'll move on to limits. And then Wednesday, we will work with continuity and polar limits. Thursday, with whatever we need to wrap up, we'll do, and then with the rest of the time, you'll have some time to work and study. Don't forget about your homework packet. Don't forget about the WebAssign. Yeah, have a great weekend, everyone, and I'll see you on Tuesday.